Okay, today we are taking an absolutely mind-bending journey, and it spans the most extreme scales imaginable. We're going to start way out there, looking at the massive, violent scale of neutron star mergers in the deep cosmos. And then, we're zooming all the way down to the microscopic, incredibly fleeting decay of a single, highly unstable isotope. Because here's the crazy part. By understanding what happens in the tiniest fractions of a second inside a single atom, we are literally rewriting the recipe of the universe.
So, here's our roadmap for this exploration. We'll start with the cosmic element mystery. Then we'll meet our microscopic hero, Cadmium-132. After that, we'll dive into the Isolde experiment at CERN, explore a new nuclear model, and finally, zoom back out to see how this is reshaping the universe.
Part 1. The Cosmic Element Mystery. The Forge of the Universe. All right, let's dive right into this massive, universally relatable topic.
Think about the gold in a wedding ring for a second, or the rare earth elements like the ones sitting inside the smartphone you might literally be holding right now. We totally take them for granted, right? But it begs a huge question. Where do the universe's heaviest elements actually come from? I mean, they aren't made in standard stars like our sun. They require an environment so extreme, so insanely rich in subatomic particles that it almost defies imagination.
The answer lies in something called the rapid neutron capture process. Just imagine a massive cosmic traffic jam happening during a cataclysmic event, like a neutron star merger. In these violent, chaotic environments, atomic nuclei are basically bombarded with neutrons so fast that they capture them and swell up into heavier and heavier elements before they even have a chance to decay. But, here's the catch. To figure out exactly how much of each heavy element is produced in this cosmic traffic jam, physicists have to rely on models. And, as it turns out, our current understanding of this rapid process has a major flaw hiding right in plain sight.
Which brings us to Part 2, Meet Cadmium-132, the cosmic bottleneck. To find that hidden flaw, we have to look incredibly close.
Let's take a look at the incredibly brief, violent life of Cadmium-132. We're dealing with a nucleus packing 50 protons and 82 neutrons. This is a highly unstable region that physicists like to call southeast of the magic Tin-132 isotope, and Cadmium-132 acts as a crucial waiting point in the R process. Check out that half-life, just 84 milliseconds. I mean, in the literal blink of an eye, it undergoes beta decay, drops down to an excited state of indium-132, and immediately kicks out a neutron to become indium-131. The exact speed of this specific decay, that's what dictates how fast the entire cosmic traffic jam clears out.
And well, here is the huge scientific hurdle. The old standard global models, specifically ones like the widely used FFDM-QRVA, have been secretly flawed this whole time. When calculating the masses and beta decay rates for these highly exotic nuclei, these older models consistently guess that the isotopes survive a lot longer than they actually do. They overpredict the half-lives. Think about it like this. If your map of a traffic jam says the cars are stopped for a full second, but they're actually speeding off after 84 milliseconds, your final calculation of how many cars made it through, or, how much heavy material was forged, is going to be completely wrong.
Part 3. The Isolde experiment, zooming into the micro-universe. So how do we actually prove those long-standing models wrong? We need hard data.
Getting that data requires absolute precision, and that's exactly what the team achieved at CERN's Isolde facility. Let's break down this incredibly intense methodology. Step 1. They fire a 1.4 giga-electron-volt proton beam into a uranium carbide target that's heated to a blistering 2200 degrees Celsius just to induce fission. Then, step 2. In the middle of all that radioactive chaos, they use highly targeted laser ionization. This lets them selectively grab just the cadmium-132, filtering out nasty contaminants like iodine and cesium. And finally, step 3. They deliver these super elusive ions to a decay station and measure the emitted neutrons using an advanced array of plastic scintillators, which they call Vandal. And the data they managed to capture from this is just spectacular. There is a massive spike right around 54 nanoseconds on the time-of-flight spectrum, and that corresponds to a huge fraction of neutron emission concentrated right around 2.0 mega-electron volts. This right here, this is exactly the fingerprint researchers were hunting for. It proves that a deep neutron transformation is dominating the decay. Specifically, a neutron from way down deep below the Fermi surface is transforming into a proton. It's definitive, undeniable physical evidence of exactly how this atom breaks down.
So the absolutely crucial takeaway is this number, 100%. By combining their neutron data and observing a complete lack of gamma transitions in the indium-132 states, the researchers confirmed that the beta-delayed neutron branching ratio for cadmium-132 is a full 100%. This is a game changer. Older estimates from past models and experiments guessed this was somewhere around 60%. Pinning this down to a flawless 100% completely corrects the record, and it provides the exact anchor we need for a brand new theoretical approach.
Part 4. A new nuclear model, the paradigm shift. Now, armed with this pristine data from CERN, physicists can finally build a new framework.
This really sets up a classic David versus Goliath conflict in the world of nuclear physics. On one side, you have Goliath, the long-accepted global models like FRDM, QRPA that everyone has been using for years to calculate the R process. But as we've just seen, they overestimate half-lives and wildly underpredict those neutron branching ratios. On the other side, you've got David, the new large-scale shell model, or LSSM, which utilizes an interaction called N3LO. Because this new model actually tracks that deep neutron transformation we just found the fingerprint for, it provides a vastly superior, highly accurate representation of reality.
And the comparison brilliantly illustrates the aha moment for the researchers. When looking at decay half-lives across different atomic numbers, the new, large-scale shell model beautifully hits the experimental data, those actual confirmed physical measurements. On the flip side, the old FRDM model wildly misses the mark. It creates this zigzagging seesaw of totally inaccurate predictions. The new model just completely fixes the waiting point timings.
Part 5. Reshaping the universe. Zooming back out. We've spent a lot of time in the microscopic world of milliseconds and nanoseconds, and now it's time to see how this micro measurement reshapes the entire cosmos.
Let's look at how this builds our completely new map of the universe. When researchers took these new, much shorter half-lives and the accurate branching ratios from the LSSM and plugged them back into a simulation of a neutron star merger, the very abundance of elements in the universe shifted. The new calculations show a totally different reality. Because cadmium-132 and its neighbors actually decay way faster than we thought, they speed up the flow of material initially, but then they create a massive material holdup right around atomic mass 130. And this creates a profound cosmic ripple effect. First off, it noticeably depletes the abundance of elements just before that atomic mass 130 peak. And because of that downstream holdup we just talked about, the entire chain reaction is totally altered. The incredible result here? It actually decreases the total amount of the universe's heaviest elements, the actinides, things like uranium and plutonium, by roughly 10%. Just think about that for a second. By measuring the 84-millisecond life of a single cadmium isotope, we realize the entire universe contains 10% less of these heavy exotic materials than all of our previous textbooks claimed. The literal recipe of the cosmos has been rewritten.
Which leaves us with this final, honestly thrilling thought. If correcting the decay rate of just a few isotopes near a shell closure can alter our calculation of the universe's heaviest elements by a full 10%, what other cosmic secrets are currently hiding inside the smallest, most unstable nuclei? It's a really powerful reminder. If we truly want to understand the vast macro universe we live in, we absolutely have to master the microscopic one first.